Hello everybody, good evening, and hello from Pittsburgh, Pennsylvania. We're doing Ask Math Anything, which means that you ask anything, hopefully it's about math, and I try to answer anything. If you haven't been here before, the way this works is that people ask math questions in the chat, and I try to choose questions that I think will be most interesting to the widest possible audience, where we're kind of focusing on people who are doing the kinds of math competitions that you might see in middle school. Although actually, because these are hard questions, typically they go beyond the middle school. I see people are talking about green shirt. You want to have me wear a green shirt. Maybe at some point in the future. Let's go and do some mathematics first. Okay, what do we have here? So I often have a moderation team which helps me out. I'm not entirely sure they're here tonight, so I'm just looking at what we have here inside. Okay, so I see that there's some questions here which are involving number theory. There's some questions here which are involving geometry. Again, I'm going to try to adjust the level of this so that we can do it as well as we can to match as many people as there are. I'm scrolling through these particular questions as well to go and see what else we have. I will say, I see a quick question that came up here. Should we use spaced repetition when learning math? I actually think the better way to learn math is not to learn by memorizing, but to learn math where you learn how to think about new things, like what we're doing right here. So when we're thinking about new things, you don't have a repetition in the first place. So I think that the exact opposite of spaced repetition is even better. Oh, Julie Z has an interesting question, but that's something that was from my mock AMC8. Were you at that live stream already, Julie Z? I did something with Fibonacci's, and there was something about the last digit of 0. I'm actually a little bit curious. If people here were not in that live stream, I'm very happy to go and talk about that question, because I really like it. This was a question about Fibonacci numbers. Please type into the chat because I can see exactly what you're typing here. If you've seen that problem before of the Fibonacci number, which is ending in 0, followed by some other Fibonacci, if you've seen that before and seen the explanation, let me know. Some people were there. Okay, so I won't do it again because that would just be a rerun. Meanwhile, I'm looking. Oh, it looks like people are typing a lot of those questions who were inside that stream. Well, you know what? Let's just do that one quickly because that was a tricky question anyway. Okay, so let me go and discuss that one. Only because it's the question I was the most happy with from that particular mock AMC8 which I wrote and shared all over internet. So this question is a very simple concept. It just says, just suppose that you wrote down some Fibonacci numbers. If you wrote down a bunch of Fibonacci's, and for all of these Fibonacci numbers, you only wrote down the last digit. So, 1, 1, 2, 3, 5, 8, 13, so I'm just writing the 3. Then the next one's 21, and so on. Suppose you wrote it for a while. I guess it keeps writing for a while. And at some point you see 0. Then the question that I asked people was, what could possibly appear next? Well, the question I specifically had asked is, which of the numbers from 2 through 6 could appear next? And since this is this Ask Math Anything live stream, I'm just going to write question mark. We're going to do this more generally, okay? So the question is, what could possibly appear after the 0? Well, it turns out that there are some numbers that cannot appear after the 0, which is very interesting. Let me first say, suppose that we had what was after the 0. Suppose it was even. The claim is this is terrible. The reason is because, you see, if somebody told you a bunch of Fibonacci's, and if they told you, here's a 1 and here's a 3, there's a way to know exactly what's before it. How? Well, you see, whatever is before it, last digit of what's before it, whatever is before it, it has to be something which plus 3 ends in a 1. Does anyone know anything that if you add 3 ends in a 1? Well, you only have one choice. It's a number that ends in an 8. So you can actually go backwards on the Fibonacci sequence as well. So now suppose that I had 0 followed by an even number. Hey, if I have 2 even numbers in a row, 0 is an even number, what can you tell me has to be true about what's right before there? Well, it has to be something plus an even number gives me an even number. That means that this number is forced to be even also. Uh-oh. it's contagious. If I have two even numbers in a row, then the number right before has to be even. Now I have two numbers in a row, both even. The number before has to be even. It's contagious. It goes all the way, and it tells me that every Fibonacci number in the world is even. How many people believe this? Is it true that all the Fibonacci numbers are even? Oh, no, of course not. They start with 1. So what that means is that it cannot be even. This is an example of a proof by contradiction. Because I've just gotten the contradiction. I found out that if it's even, no good. I would have that all of them are even, which is false. So that's how I know that this number is not even. Well, there's something else that I can also rule out. So far, I'm trying to figure out what is that thing that's right after the 0, not a 7. What's the thing right after the 0? Well, I know so far that it's not even. Because if it was even, then I'll just keep going up and it's like they're all even. Does anyone know another digit that I can knock out? There's an odd digit that I can knock out also that uses the same kind of logic about contagion. If something ends in 0, oh, it's definitely even. I know that for sure. Does anyone else know anything else that is true about a number that ends in 0? It's definitely a multiple of not just 2, but also a 5. So actually, this number is a multiple of 5. Now, what if I had two multiples of 5, one after the other? Suppose that this ended in 5. Could it end in 5? Well, if it ended in 5, then I have a multiple of 5, and right before it is a multiple of 5. So before that is whatever plus 0 gives you a 5. Well, actually, think of it this way. We have whatever plus a multiple of 5 gives you a multiple of 5. So that means that has to be a multiple of 5 also. The only way to add a multiple of 5 and still get a multiple of 5 is to start with a multiple of 5. Uh-oh. So that means that if I keep going upwards, this is also a multiple of 5. So at this point, I get contagiousness of two multiples of 5 in a row give me a multiple of 5. Two of these multiple 5s in a row, two multiples of 5 in a row, next one up. And it goes on forever, and they're all multiples of 5, which is bogus. So at that point, that means that this, unfortunately, is not a multiple of 5. So no way. This is also a contradiction. We can't have a 5. So now we know it's not even, and also not a multiple of 5, and also not a multiple of 5. Remembering what we're trying to solve here, we're trying to figure out what is this as a Fibonacci number, what is the possible last digits. And oh, by the way, I'll answer another question. There's a question about when do these live streams start? Is there a schedule? I'll tell a bit more about that at the very end of this live stream. But unfortunately, we're not going to have more live streams for a while for various reasons. I'll tell a bit more of the reasoning towards the end. So let's just go and have some fun with this one. Okay? Because what we've just found out is that whatever goes here, it has to be not even, it has to be not a multiple of 5. So what options are there? It's really interesting. For the Fibonacci numbers after the 0, you have pretty restricted options. So far, the only options that seem to still be surviving are 1, 3, 7, and 9. And what I'll say is that if you actually go and do these, and write this out for a while, you will actually see 0 followed by 1. Well, I can actually tell you there's a place you'll find 0 followed by 1. It's right here. If you think about what's right before these two, what number would make sense to put there so that that plus 1 was equal to 1? A 0. So actually 0 followed by 1 already appears in the Fibonacci sequence. That one you can see. And if you just do it for a while, you will find out that you can get 0 followed by 3, you can get 0 followed by 7, you can get 0 followed by 9. And the only ones you can't get are these things which are 0 followed by even or 0 followed by multiple of 5. It's pretty cool. Okay, more questions. So I see my moderation team is now also here, so I can go and see what have they picked up while I was just talking about this. All right. Okay, so I'm looking at these different questions. Okay. Is that a good question to do? Ooh. I see a very interesting question to say something about, which might be more difficult than what we want to talk about today. But I'm going to write it down anyway, okay? So there was this question here. Somebody, Rational Pi, has asked, prove that if I take a sum of numbers, the sum is in the middle, 1 over 1001 plus 1 over 1002 plus 1 over 1003, keep going, all the way to 1 over 3001. We're supposed to prove this is between 1 and 4/3. Okay, so I want to talk about this because it actually is related to something very, very deep and quite hard. But nevertheless, let's see what we can do with some simple ideas, okay? So some simple ideas would be, if I want to show that this is bigger than something, one naive way to do that would be to say, let's see how many things there are and multiply it by the smallest thing there, right? Because if I have all these numbers, how many are there anyway? From 1001 to 3001, how many of them are there? Well, you can figure this out. How many of these numbers are there? 1001 to 3001. If I subtract 3001 minus 1001, it's 2000. So there's 2000 of them, right? Well, not really. You always have to add 1 when you do that kind of a calculation. 2000 is the number of steps that I take to go from one to the other. But if the number of steps is 2000, the number of numbers is one more than that, because I start from something, take a step, and then a step, and then a step. So there's 2001 of them. Okay, so at that point, the simple approach would be to say, what's the smallest of them? The smallest of all of these numbers is 1 over the biggest. So the smallest is this 3001. So I do know that, this 1 over 1001 plus all the way to 1 over 3001, that's bigger than 2001 divided by the smallest one. Oh man, that's not 1. So I have something that is bigger than. It's not good enough. I'm supposed to prove that it's bigger than 1. But, okay, I'm close. This is around 2/3. Is that enough? Can I get partial credit? Give me 2/3 of the points? I don't know. We'll see. So you'll see another way. There's another way I want to talk about this. But this is just saying like somehow, okay, right, it's around like that. Well, how about the other side? The other side, I could try to say, let's compare it to 2001 times the biggest one. Okay, so on the other side, if I want to find something that's bigger than it, I can just compare as if all of them were the biggest one. The biggest one is 1 over 1001, so that's 2001 divided by 1001. Well, that's not good enough either. I need something which is less than 4/3. And if I want something less than 4/3, this is unfortunately around 2. So unfortunately, I didn't manage to prove it, but I got close. Actually, I got what's called a constant factor approximation, which means that whatever I got from my bounds, the smaller and the bigger bounds on this sum, are, close up to a multiplicative factor, which is not too far off. All right. So unfortunately, this technique doesn't work. Not precise enough. But it turns out that this is related to something else. So let me go and look at these numbers again. And if I have 1 over 1001 plus all the way to 1 over 3001, well, I'm going to draw some rectangles. But I'm going to draw the rectangles against a graph. Now I just, for fun, want to graph 1 over x. Okay? So I'm going to graph 1 over x. Actually, I want to graph 1 over x and think of it like where this is all the way out by 1000, x equals 1001, x equals all the way to 3001. So the graph of 1 over x looks something like this. Actually, it's not to scale at all. So here's what I'm going to do. It goes down like this, and then like dot, 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 because I'm going to imagine that the axis is broken here, okay? So here's like small numbers, and here's like, now I take a fast forward all the way out to like where it becomes 1000, and then 1001, and then 1002, and so on, dot, 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 okay? And it's going to go another break in the graph, and it's going to go all the way out to 3000 and 3001. That's 3001. And let's pretend that the graph, by then has gone and it's very slowly, that's supposed to break in the graph too. So it's like it's very slowly decreasing. And then it decreases some more. But it's just always decreasing, okay? Now, why am I doing this? I'm doing this because the question was asking about this 1 over 1001 plus all the way to 1 over 3001. Well, let's draw some rectangles. I want to draw some rectangles that will show what this is. Give me something that's, I'll use the rectangles to give me something that's bigger than this. I'm going to draw a vertical line up from the 1001, touch the graph, and then I'll go left. And then I'll do this. The 1002, I'll go up to the graph, and then go across, and then go down. And if you look very closely on your screen, you'll see there's a tiny gap there. And there's a tiny gap there too. Okay? And I have more rectangles. The more rectangles are just going across like this. Okay? And then over here at the end, I also have the rectangles. And it goes up to there and it stops. All right? So no more purple rectangles this way, no more purple rectangles that way. Can anyone tell me what the interesting relationship is between this sum, 1 over 1001 added all the way up to 1 over 3001? What's the relationship between that and these rectangles? These rectangles have interesting heights, by the way. What's the height of the first rectangle? Well, I went from this 1001 and went directly up and then across. So the height of the very first rectangle, if the graph, I should have said, what's the function? The function is 1 over x. Okay? I did say that, by the way. I just want to write it here, just so that anyone who came, yes, the fun stuff says area of the rectangles. The sum of the area of the rectangles is exactly this. This equals total area of rectangles. Okay, well then that means it might be kind of interesting if I could figure out something easier to estimate, where that easier to estimate thing is bigger than that. Remember, I'm trying to show that this sum of these numbers, I want to show it's less than 4/3. Is there anything I could use? Any other thing that you could imagine that looks like it's bigger than the sum of the rectangles? Juliet Z, isn't this kind of like integral calculus? Well, obviously you're not a middle school student. Or actually, I shouldn't say obviously, but it's like you seem to know something that you learn in calculus, and that's exactly where this is going. So actually what's going on here is, if I want to know something about the sum of these numbers, well, actually, there are two things I want to say. This is actually definitely less than the area underneath 1 over x from 1000 to 3001. Okay? And also, if you look at it, it's pretty darn close. It's very close to that area, which is also going to be very interesting. It's going to be very useful. All right, well, let's actually do it. So in order to actually do it, what I need to say is, I now know that the sum of these areas is less than the area underneath this green line. So I now know that it's less than the area if I draw this picture. And I just want to know from 1000 to 3001, and I have this 1 over x, and I actually just care about the area between these two. Now, at first, this looks even worse. Like, this is like way, way, way harder than just adding up some fractions, isn't it? Wouldn't it be more fun to just add up fractions? Well, no, I hate adding up lots of fractions. But it turns out that if you take a class called calculus, usually in high school in the United States, then you'll learn that this is a really easy problem. And don't worry, if you haven't taken it yet, don't worry. It's just something that you'll learn later. But if you have this question, this is remarkably easier. It's related to something called the natural logarithm. And in fact, this is called the integral calculus. And it doesn't matter if you haven't learned it before. I just want to show you. It's really interesting that it turns out that this is the wrong pen. It turns out that this area right here is exactly the natural log of 3001 minus the natural log of 1000. Now, that's way more difficult than the kind of math that people usually do in middle school math contests. But that's just, I want to give you a taste of the fact that that's where a natural log comes from. Isn't it cool that if you just go and take the 1 over x function and you go find areas underneath it, that the area between two particular x coordinates on the 1 over x function is actually the difference of natural logs, of the natural logs of those two endpoints. And now, if you know what a natural log is, the difference of logs is the log of the quotients. So this thing is approximately the natural log of 3. 3001 divided by 1000. And the natural log of 3, hopefully, is less than 4/3. Like that's how you would be able to do this. Strictly speaking, I would want to know what's the natural log of 3.001. Well, let's just do that. It's equal to natural log of 3.001. And you can punch that into your calculator or something. That's going to be 4/3. I'm almost positive it's going to be less than 4/3. Okay, so that's like this so-called upper bound. And for the lower bound, it turns out that you can do the same thing, where instead of drawing these rectangles, just draw the same idea, but instead of going up and going to the left, go up and go to the right. Oh, cool. Did someone say it's 1.009? That can't be right. Natural log of 3.001 can't be 1.009 because natural log of E is 2.718 whatever. That's 1. So natural log of 2.718 whatever is around 1. This is more than 1, but it should be okay. 1.09, that one I can maybe believe. I don't actually know off the top of my head, but 1.09, pretty good. We had to show it's less than 4/3. Bam, that did it. Okay. Yeah, I wasn't able to, it's not that I wasn't able to avoid using calculus. I can also do this in other ways where we break the sum up into smaller pieces, but I actually wanted to do this intentionally to show you that there's this very remarkable relationship. And there is some formula of factorial that doesn't require recursion. That person is talking about the idea that you can also think of what's called the gamma function, which also goes back to these areas under curves, which have something to do with factorials also. But let's not go into that on tonight's live stream. Basically, this is what I wanted to say for this. And if you want to show this sum is bigger than something, go up and to the right. And suddenly if I go up and to the right, I'm just afraid of spoiling my diagram, so I'm not drawing more. But if you go up and to the right instead of up and to the left, then all the rectangles hang out over this curve. And so actually, it turns out that the sum of those areas of the rectangles is then bigger than the area under the curve from here, 1001, all the way to here, which is 3002. And then you can use the same thing. And this is actually very, very tight approximation for this particular sum. It will basically be around natural log of 3. Okay, enough of this for now. Let's go and do some other questions. Hopefully will be questions that will be more approachable. What else do we have? Let's see what we got here. Oh, okay. Rohan has a question. Rohan Agarwal says, we have a number. Let's see. A number has exactly 143 positive factors. Wow, what a crazy number. So a number has 143 positive factors. Let's just say factors. Okay. 143 factors. And it can be written as m times 3 to the power n. M times 3 to the power n, where the m and the n are positive integers. Okay? Well, it says where they are integers. I guess maybe it could be 0. We'll see. Oh. I actually think that they probably mean, no, of course, it can't be 0. Positive integers can't be 0. Okay? So oh, wait a second. No. So I was saying that they have to be positive integers. The problem says they have to be integers. I'm a little worried that actually if you're allowing 0 there, you might have multiple answers. But let me keep writing. So m times 3 to the n. And the question is, what is 1 over m plus 1 over n in simplest terms? Okay? And so it looks like you want to have a definitive answer. But here I'm going to be give a little bit of a warning, which is I'm pretty sure that you want them to be positive integers. Because if I'm allowing them to be 0, for example, I could go and make n to be 0, and then suddenly this is gone. And then it's just like m, right? So there's probably lots and lots of choices. There are probably lots and lots of numbers in the world that have exactly 143 factors. In fact, if I take any prime number to the power 142, any prime to the 142 has 143 factors. You know why? Because I can tell you exactly what they are. They are the prime to the 0. That's also called 1. You have the prime to the 1, prime to the 2, prime to the 3, prime to the 4, prime to the 142. And since I have all the powers from 0 to 142, there's 143 of them. Okay? Uh-oh. So somebody, there's more stuff. Rohan's telling me m also has to be a power of 2. Oh, thanks, Rohan, for giving more details for this question. So actually, what you want to do on this question, well, let's not erase. Let's just say any prime. So there's like all these multiple answers. And actually, what you care about is that where you have m is a power of 2. Well, you know what? I actually will go and write that here. Okay? So I'll write it is 2. I'll just do it differently. Okay? It's 2 to the m times 3 to the power n. Okay? And furthermore, the way I'm going to do this is I'm not going to ask what is what. Well, do I want to ask that way? Well, look, let me just do what you said. Okay? I'll write the m. So let's undo all of this stuff. M, please come back. Great. And I'll also write the parenthetical comment right here, which is that m is power of 2. Ah, now I see why you're saying this thing where, and neither can be prime. Well, you say m has to be a power of 2. You're saying there's multiple answers even if m is a power of 2. Are you sure? This thing might be okay now. The reason this might be okay now is because actually the question is asking not what are m and n, but what is 1 over m plus 1 over n. So I think that there might be 2 solutions for m and n, but they might give you the same answer for 1 over m plus 1 over n. I think. Yeah, I think. We'll find out soon. Okay? So actually this thing just generalizes. The concept that if I have a prime to something, I have this many factors, and the number of factors is 1 more than the power. Well then actually if I multiply together any bunch of primes raised to powers, the number of factors is just take all the powers plus 1 and multiply those numbers together. That's combinatorics. Okay? So let's just go and talk it through right here. So in general, if I have a power of 2, wait a second. No. I don't like this. The reason I don't like this is because I think actually it's not going to have the 2 solutions to be the same solutions, same final thing, unless it is 2 to the m. Okay? So I actually think that we should actually write this as 2 to the m. I am going to make that change. 2 to the m. Clear this off. Okay? I think this actually is going to give a unique answer. And so let's just see how you would do this. Well, using the same philosophy here, if I have these 2 primes raised to various powers, well, then the number of factors that you can have from this number is that every factors are 2 to the power something times 3 to the power something else. But your optionality here is that inside the 2 to the power something, those can be 0, 1 up until m. And the 3 to the power something, those can be 0, 1 up until n. Okay, this is cool. So in that case, this is telling me that the number of factors I can have is just how many choices I have for the blue power times how many choices I have for the green power. So that means the number of factors is just m plus 1 times n plus 1. So there are m plus 1 times n plus 1. Okay, well in this case, now if I know that m plus 1 times n plus 1 is 143, I guess I have to factorize 143. And that's nice because I can see that that's a multiple of 11. See, 143 is just 11 times 13. The way that you multiply things by 11, if you have a 2-digit number multiplied by 11, is you pull the digits apart and you put the sum of the digits in between. So 13, 1, 3, and then the 1 plus 3 is 4. That's actually what happens if you just multiply it, like 13 times 11. You'll see that's what happens. Okay, so in that case, what happens? So I have to have that m plus 1 and n plus 1 are 11 and 13. I don't know the order, but that just means that m and n are 10 and 12, right, in some order. And that's why this thing just asks what is 1 over m plus 1 over n. Well, it doesn't matter what order they are in, okay? So m and n are 10 and 12 in some order. And finally, we finish with 1 over 10 plus 1 over 12. Doesn't matter about the order. Oh no, for me this is the hardest part of the problem. What's a good common divisor? Not common divisor, a good common multiple. Well, I think I can do 60. Okay, so I have 6 over 60 plus 5 over 60. I think it's 11 over 60. And I think that's the answer to the question. Okay, more questions. What else do we have here? It's 8:30, so we have like 15 more minutes. Let's see what came in. I'm trying to find the best ones that can be interesting to a broad audience here. Whoa. Okay, here's a geometry question that I don't know how to do, which is why I want to do it. Okay, so this is from Selena Breinholm Milde. Okay, and we have a large square field with a side length of x. I guess fields are green, so let's use green. Large square field, side lengths are x. What else do I know? I also know that the distance from, there's a farmhouse inside, and the distance from the farm to 3 of the corners of the field. Oh, okay, I get it. So the farm is so small. I'm interpreting this question to say that the farmhouse is just a dot, because I was like, maybe I should draw like a big farmhouse inside, but no, because it's a huge square field, and the distance from that farm to 3 of the corners is 7, 3, and 5, respectively. Okay, what does that look like? Maybe that looks like this, 7, 3, and 5. Wow, this is hard. No, it can't be there. It has to be a bit closer to this side. Maybe this. That was bad straight line. Let's try again. The problem with a straight line is if you start going in the wrong direction, you can't change direction because it's supposed to be straight. So that's 7. That's 3. That's 5. Okay, and then the question says, go and find x. Okay, well, when I look at this question, the first thing I want to know is it unique? Is there a definite answer for x? Let's see. So if I have a 3 and I have a 5 and I have a 7, does that always force there to be exactly one way to do this? Well, actually, as I'm looking at it right now, I'm thinking that, maybe we try to throw some variables into this and see what happens. The reason is because, maybe variables will work. But the reason is because we could use the Pythagorean theorems. So these are all slanted lines. And so my first gut instinct would be, let's go and throw some variables down and see what happens. Okay, maybe this is not the most efficient way to solve it, but we'll find out the hard way. Okay, so let's draw some perpendicular lines here and here. Now, x is a variable. I don't know what it is, but I'm excited about this particular approach because I'm going to end up taking something squared plus something squared. All right, what will give me the fewest number of things that I have to have as variables? I don't know. So let's just go ahead and start. So when I look at this, I say, you see, each of these two sides got cut by something. So I guess I have an unknown here and I have an unknown there. Let's do that. So I have an unknown part, which is here. I'll call it A. And an unknown part which is here, which is called b. And since the whole thing is x going across, then this unknown part is x minus a. Please understand the x to mean it goes all the way across. And in order to minimize confusion, I'm going to do that by now labeling the x down there. Right? So x is this way, that is a, that is x minus a. I can do the same with this side. That x is the whole thing. So this side is x minus b. Okay, let's go ahead and use the Pythagorean theorem a bunch of times, and let's see what happens. And meanwhile, the fun stuff says x should be greater than 10. Maybe that's the case. We'll find out. But over here, I just want to be like, I don't exactly see why it should be greater than 10 yet, but I'll say that if I look at this, then I may as well just use some variables, see what happens. I mean, I'll say, wait a second, are you sure it's greater than 10? I think it's the other way around. You're using the triangle inequality. I see that there's a 3 and there's a 7. So in fact, the length of this thing is less than or equal to this one plus that one, right? The shortest path between 2 points is the straight line. So in fact, the x is less than 10. And furthermore, x is also less than 8. So So if I look over here, this x is the shorter thing than going 3 and then 5. So x is less than 8 also. I think you were trying to use the triangle inequality, but you used it the other way. No problem. Let's just keep going. So if I have this thing now, let's go and write down some equations. Because I know that a squared plus b squared, this thing here is also b. A squared plus b squared is 3 squared, which is 9. So some equations. A squared plus b squared equals 9. I'm not sure I have enough information, because over here I see, oh, maybe I do, because I have 3 variables and 3 unknowns. So a squared plus b squared is 9. I also can get this thing, which is 25, where I have a b squared plus an x minus a whole thing squared. I'm going to expand x minus a whole thing squared already. X squared minus 2xa plus a squared, and then plus the b squared is equal to 25. Ooh. You know why I'm a little bit excited by this? I like to see that there's an a squared plus b squared which appeared, and it's also there. So I'm going to end up using like a weird mishmash of things like substitution or whatever to try to solve this problem. And I already see that I could potentially make this cleaner. You know, I'm just going to do it right now just because I feel like it. Because to me, no matter what, if I remove the a squared plus b squared and replace it by 9, that should be a good thing anyway, because it's just less messy and it's replacing with a number. The number should be more convenient anyway. So this thing is 9, right? That piece is 9. But if that piece is 9, well then actually I can just subtract 9 from both sides. And I get simply this x squared minus 2xa is equal to 25 minus 9, which is 16. That seems simpler, so I'm just going to write that down. Oops, let's go back. Oh yeah, well, why not? Let's get rid of that. So that seems simpler. So I'm going to replace that with x squared minus 2xa is equal to 16. Well, I think a similar thing is going to happen over here, because probably we're going to have symmetry. Well, not probably, we definitely will have symmetry. We have symmetry across, how do I flip my hand? Yeah, across this way, all right? So now I have this part which is a squared and this part which is x minus b whole thing squared. If I write that out, x minus b whole thing squared is x squared minus 2xb plus b squared and then plus the a squared. That's equal to 49, which is the 7 squared. Oh, look, again, I have this b squared plus a squared, and that was the 9. So if this thing is 9, subtracting 9 from both sides, I'll get 40 on the right side. So now I have x squared minus 2xb is equal to 40. Now is the art form. Okay, now the question is, how could I try to solve these? I have 3 equations here and 3 unknowns. In principle, unless these equations are so-called degenerate, where like one of them is created from the others, that's a very deep area of math that this is in now. It's called algebraic geometry, but don't worry, we won't go there. As long as these aren't degenerate in some way, I should be able to find some finite set of solutions. So, okay, what could I do? How could this be nice? I mean, I could start to subtract things. That's not fun either. So let's see. When in doubt, drink some water. I do see that if I added the a squared and b squared back and added this all together, I'll get an x minus a whole thing squared plus an x minus b whole thing squared. Oh. Wait. This is not bad at all. Hang on a second. I'm coming back here. Because if I come back here, it looks to me... No, it doesn't look that good. Over here, I have an x minus a whole thing squared, an x minus b whole thing squared, an a squared, and a b squared. That's no fun. Maybe let's add it over here, and then I'll have something interesting. X minus a whole thing squared plus an x minus b whole thing squared I could get. Something is smelling a little bit good about doing that. Okay, so here's what I'm going to do next. I'm going to go and add this equation and both of these equations together, because I see that I can make an x minus a whole thing squared by stealing that a squared. And I can, if I add them all together, I'll also get a b squared, which joins in here to make an x minus b whole thing squared. And I'm starting to see some patterns come together. So I'm going to add up all 3 equations. Okay, and if I add up these 3 equations, add up, then I'm going to get x minus a whole thing squared plus an x minus b whole thing squared is equal to whatever they all add up to. Okay? And what they all add up to is something. What is it? 9 plus 16 is 25, 65. The reason I'm kind of liking this thing. Oh, somebody asked, how did you get a squared plus b squared equals 9? Some person asked. Well, it's because this is a and this is b. And a squared plus b squared is 3 squared. So it adds up to 9. Okay? So that's why that comes. They're all from Pythagorean theorem. Okay? So now, if I look at this thing, the reason I like it is because I have an x minus a squared and I have an x minus b squared. I know what those two add up to. I also know what happens when I take, like, the x minus a squared. Basically, I see 4 things, and I'm adding them up in some kind of a loop. I don't know if I still don't know if I like this yet. I have these 4 things, and I'm adding them up in a loop. What I mean by adding them up in a loop is because I have an a squared, a b squared. I have an x minus a whole thing squared, and x minus b whole thing squared. And if I drew a little loop, where I say I have an a squared, let's draw a loop. I have an a squared, I have a b squared, I have an x minus a squared, x minus a whole thing squared, I have an x minus b whole thing squared. Okay? Now if I have this loop, I know the sum of these two, a squared plus b squared, that adds up to 9. Oh, let's just draw some funny diagram. See if this makes any sense. These add up to 9. I have that if I add if I look at this thing here, I have an x minus a whole thing squared plus a b squared is 25. So this thing adds up to 25. This is my new diagram. Okay. Then I also have that if I do this one, which is x minus b squared and then plus the a squared, that adds up to 49. And I also have that if I take the x minus a squared and the x minus b whole thing squared, those add up to 65. Is this useful? This was slightly motivated by the fact that if I have 3 equations and 3 unknowns, and I know that, 2 of them add up, plus 2 of them add up, plus 2 of them add up, if I know each of those sums, I can work everything out. So this is making me wonder, can I do the same with 4 equations and 4 unknowns, where I just know every single pair? Well, if I try to use the same kind of concept, well, if you just add up all of the equations together, then I will actually get double of everything. Is that useful? Basically, I can find out what is a squared plus b squared plus this thing squared plus this thing squared by just adding up all of these 4 numbers and dividing by 2. And that's because of the same fact that if I have 3 unknowns and I know the pair plus this pair plus this pair, if I know each of the sums of the pairs, then if you add up all of those sums, it just happens to count each of the numbers twice. So looking at this same idea, if I just added up all of these equations together, then that would also be good. And indeed, this is what Rohan is suggesting. Replace these by y and z. That's the same principle, right? I could do that, but I'm afraid that if I do that, I might miss some of the important information, which is that they actually have more relationship than just being a y and a z. Maybe that's what I'll end up doing in the end. But unfortunately, it doesn't seem to me that it's that useful right now to know the sum of all of them squished together. If I know all of them squished together, that's not useful either. Because then, unfortunately, what I'm going to get is that, unfortunately, what I'm going to get is just some more information which is not going to be able to nail down any one of those numbers. In fact, that information that I get if I just add them all together, I could also get by just adding this green one and this yellow one. By the way, this trick of doing this sum around, what you're seeing is that it's actually only useful if there's an odd number of unknowns. Okay, let's see. So what else could we do here? Oh yes, and thank you very much, Lainey, for pointing out that because of this, I in fact even know the 4th diagonal. I could work out this 4th diagonal, which is pretty cool. This 4th diagonal is the square root of 65, because that's going to be that squared plus this squared with a square root. So that's cool. We know how long this is. Now, if only we could figure out what x is. Yeah, maybe we could try doing trig, but I'm like, I do have 3 equations and 3 unknowns. In the worst case, I could do some terrible, terrible substitution, which is in fact what trig would probably be useful for, because I could maybe try to use a cosine for a. Let's see. When in doubt, drink some water. And then think again, is there anything else we could do that will at least, like we could brute force this by substitution, but is there a nice thing I can substitute? I don't see that. So nice substitution I don't see. By the way, this is a famous type of question for which there's probably also a non-algebraic solution. Maybe we should take a pause and try to find that one. I thought I could just like beat it through with the algebra because I was like 3 equations, 3 unknowns. But unfortunately, the 3 equations, 3 unknowns, that's not so nice. Less than a minute, you're right. But unfortunately, or fortunately for you, depending on how you look at it, I sort of like to beat a problem. So now I'm facing down this problem, and now I want to know what to do. What else can I do here? 3, 5, and 7. I'm just thinking about what else we might know from the 3, the 5, and the 7. And yeah, indeed, I'm thinking of doing some geometric transformations of just like what I might do if I use a square. Maybe you can try to fold the square and see what happens. But at the moment, meanwhile, the great thing about running these live streams online is that people have suggestions that you could try, you can try adding equations. But you see, if you do this, if you add the equations, and then try subtracting, you'll actually just get back things you already had. So that's not so nice. Meanwhile, people are suggesting things like rotating stuff. Oh, you could also rotate the square. That is true. And if you rotate the square, I'd get something with like a 3. I wonder if that tells me anything. Oh my gosh, you're brilliant. Okay, I like that. Thank you, crowd. It's a great idea. Let's rotate the square. Let's take this thing and just turn it. Because by the way, you see, what I was doing is I was first being like, let's just beat this up. But unfortunately, it beat us up with algebra. So the next thing you can do is you can be like, let's be smart. So there's this nice straight line here. And if I rotate this 3 and this 5 by 90 degrees to go there, well, then the 3 and the 5, the 3 will be here and the 5 will be there, and it will actually go, and the 5 will like touch right to there because this was x and that was also x. Is this related to the British flag theorem? I don't know what the British flag theorem is, but maybe it is. So let's go and try to rotate the square. Let's do it in the next picture. Okay, so now if I rotate the square, what ends up happening is that you have that side and that side. This thing goes down. This thing goes across. And then what I have is, I had the 3 and the 5. It was doing this. This was the 3. This was the 5. And then this was the 7. But then when you rotate the square, then I can also have a 3 over here. Because I rotated 90 degrees. Actually, since I rotated 90 degrees, it should really be 90 degrees here. Okay? And this is a 3. Imagine that was a straight line. And then over here I have a 5. Imagine that's a straight line. Does this make sense? So it definitely needs to be like a 3, a 90 degrees, a 5, and a 7. Well, actually at this point, now I can do something pretty powerful. Because, you see, I just care about what is this distance, and I always think geometrically of like, is it rigid? Have I found some way that I can start to forget about parts of the problem, and it's just like, it's a certain length where I put down something of this long and this long and this long, and then I just do something and measure with a stick. The problem with the previous statement of the problem was there was nothing to measure with a stick. I don't know where to put the 3, 5, and 7 and how to make them angle. But suddenly this is saying, hey, you know what? Forget the green thing. I have a blue thing. The blue thing looks like this. 45, 45, 90 right triangle. 3 and 3. Okay? And then, that was supposed to be isosceles, but I didn't quite match the other side. Let's try again. There. And then I have a 5 and a 7 that come down. Exactly 5, exactly 7. So then this goes down by 5. And this goes over by 7. By the way, this you can do rigidly. You could actually go and grab a stick which is 3 long and another stick which is 3 long and anchor them so that they're 90 degrees. And then you could go and measure out a 5, measure out a 7. You could actually do it. And then you take a ruler and you measure how long is it from here to there. And that's all you have to do. That's the answer. Now the question is there a nice way to actually work this answer out? Because, this side here is 3 root 2. That I know. And now the question is just like, how far is it from here to there? Ouch. That also looks painful. See, at this stage, if I see this kind of a thing, I'll be like, if I wanted to know the answer, I could go ahead and use something called trigonometry. I could use something called the Law of Cosines. And that way I would be able to get you an answer for sure. The reason is because whenever you have something made out of triangles, they're stiff and they have certain angles. For example, I know that this angle here, that's 45. That's from the 45, 45, 90 right triangle. I could actually go and figure out what is this angle here. Here we're just like beating this problem up. I wonder if there's a nice solution. Maybe there is, but and probably there is. It's somehow a famous question. But we can figure this out now, because let's go and somebody said bash it out with Heron's formula. I'm wondering if that will give you a precise answer that I could solve for. I don't immediately see how that will give me an answer that I could get nicely. So I'll just say we could do it this way. Interesting. I'm also trying to think if there should be an answer which is all expressible in square roots. If I look at this, should there be? Can I think of this as something where I can write out the formula and square enough times? Maybe. But let's just go back here. So over here now I just have to be like, okay, I need to know by the law of cosines. We've gone way out beyond middle school math in this one. But how would you use law of cosines here? Well, if I don't know what that unknown is, then there's a way to write down what the cosine of that unknown is. And let's give that a name. Let's call that unknown angle. We always call it this nice Greek letter, theta. And so there's something called the law of cosines. Which says that it's sort of like the Pythagorean theorem. It says that if I take this one squared, and that's 3 root 2 squared, that's 9 times 2, which is 18, plus 5 squared, which is 25. Now you write minus 2 times 5 times 3 root 2 times the cosine of theta is equal to 7 squared, which is 49. All right. Is there anyone here who can help me out and figure out what this is? Yeah, it's like the extended Pythagorean theorem. That's right. I basically want to find out if it's some nice number. I want to find out if the answer is some nice number, and if so, I want to find a better way to do it, right? But so I have this law of cosines gives me this thing, so I could actually work out what cosine theta is. Is there anyone who has a calculator handy? This is actually how I did a lot of math contests before too. I need to go and figure out what value cosine theta has. And cosine theta is going to be, I take the 18 plus the 25 and then minus the 49. I need somebody to help me work this out. Somebody with a calculator or something handy. We need to know 18 plus 25 minus 49 divided by 2 times 5 times 3 root 2. Is there anyone who can help me out with this? Somebody has an idea. Yes, you're all part of something. Let's do it. You're telling me, is it that cos theta equals this is 0.4472? Someone told me it's 0.4472. I hope you're right. So then you use something called the inverse cosine. You can take the inverse cosine and you can find out what theta is. So the inverse cosine, hopefully someone has a calculator handy or a computer. You're telling me it's minus? Is it minus? Do I believe that? 18 plus 25. Well, that's like 43. Ooh, negative. That's a negative number, isn't it? There's a negative number. So Skylar sure said positive. I think we need negative because if I took 18 plus 25, that's going to be 43, right? So in that case, I will have a negative here. So can anyone tell me the inverse cosine? Is it 118.5 you're telling me? Oh, then my picture was very much not to scale. Not to scale, but I believe it there actually. So that's okay. You're telling me 118.5 degrees. Keep all of your extra decimal places, by the way. Whoever's doing this, you want to write theta is the cos inverse of that thing. Okay, keep all your decimals if you're using a calculator. But it's going to be around 118.5 degrees. Oh, 49 minus 43. I screwed up. Why is it 49 minus 43? Maybe I screwed up. I have a lot of trouble with this kind of thing. Oh no. Oh no. Hang on a second. It's a squared plus b squared. And then, wait a second. So people help me out here. Did I write the law of cosines backwards? A squared plus b squared minus 2ab Wait a second. 49 minus y. So first of all, let me make sure I have the law of cosines straight. What you're seeing here is that I don't actually use the law of cosines every day. So let's get it. A squared plus b squared. Why did I want minus 2ab? Let's find out. Do I believe it? The easiest way to find out, by the way, is just make the angle like 180 degrees. Okay? So let's go and check. So like if I want to check this, I'm like, let me just try this out on the most amazing triangle ever. It's called the AB straight line triangle. So C, by the way, is this C here. Ouch. Okay, what a triangle. Well, what's cosine theta here? So theta here is 180 degrees. Cosine of 180 degrees is negative 1. Okay, cosine of 180 degrees is negative 1. And then therefore, if I stick out there, I have a squared plus b squared plus 2ab. Yeah, that's c squared. It's all good. It's all good. So then in that case, somehow my memory, even though I haven't really used the law of cosines for like 20 years, I guess it's still right. Still there's a minus sign here. So actually, so far, this is still legit because that's a minus sign. So I yanked it over there. That's why it's positive sign. But that difference, you got negative. Okay. And yes, Rohan, that's right. That's a degenerate triangle. But that's how I go and test to see whether it's plus or minus. I could also try it with the right triangle. But the annoying thing is then the cosine is 0, which doesn't help me at all figure out whether it's plus or minus. Okay. Continuing on. People said this was around 118.5 degrees. Okay. So this was around 118.5 degrees. Again, it's important to keep all of the decimal points if you want to do it right. And at that point, I just want to add 45, right? Just add 45 to it. Now I have a new one, and we law of cosines it again, and then we're done. The last thing, I want to know what the answer is. It's called C. What's C? C is equal to the square root of law of cosines time. It's going to be 3 squared plus 5 squared minus 2 times 3 times 5 times the cosine of 45 plus theta. All right. Can someone tell me what this is? This is all I care about at this point. And, oh, interesting. I'm going to say, actually, if you wanted to write this all with square root signs, you can do it if you really wanted to. The reason you can do it if you really, oh, something I screwed up. Cos theta is, wait, do I have a mistake? Maybe I have a mistake. There are all these different answers which are showing up here. But I'm just going to say, if you're using your calculator, just multiply that, add, subtract, divide, blah. And then you cosine inverse. And you should have something like this. Okay? You may have used radians instead of degrees. I'm doing everything in degrees because I have 45. All right? And then after you got that answer for your theta, you just want to be like, okay, great. Evaluate this. And you should get something. Cos theta equals minus 1.4142. I'm having a little bit of trouble understanding if that's right. So is it not this one? Are people saying it's not this minus 0.44? Well, let me do a ballpark, okay? What do I have? So let me just do this in my head. Let's see what this is. So 18 plus 25 is 43. 43 minus 49 is negative 6. So the top is negative 6. The bottom, okay, let's do it. See, I don't actually have a calculator. I don't like calculators. If I do this thing, what does this become? Let's go up there. I'm going to get a minus 6 divided by 2 times 5 times 3 root 2. And I see that the 6 cancels because I have a 2 and I have a 3. So it's 1 over 5 root 2. Ooh, it's not this. This is too big. Okay? Because 5 root 2 is like 1.414. So this is around 7. So this is like 5 times like about 1.4. So it's about 7. So it's about minus 1/7. So that means it's around minus 0.142857. Okay? Oh, good. And that's coming out with people's answers. This is actually why it's so powerful to be able to do the things without calculators, because you never know if what people say is exactly right. So over here is minus 0.14. And then it's another 142. But you can see how I estimated that in my head, right? Because it should be around negative 1/7, which is around negative 0.142857. So this is pretty good. So in that case, now I need to uncosine that. What's this? Is that still 118.5 degrees, or is that different now? What happens if you arc cosine, or cosine inverse of this thing? Can anyone help me out? You would actually want to, if you're using Wolfram Alpha or something, you really want to type cosine inverse of this, like this enormous thing. What is that? People are saying 106.42. That seems more believable because, so 90, or it might be 98 degrees. I believe it's closer to a right angle. 98.13, I'm seeing multiple people are saying 98.13. So I think that does sound reasonable, by the way. It's closer to 98.13. This is approximately. The reason I think the reason it has to be, the reason this thing has to be bigger than 90 degrees is because it's a negative, the cosine is negative, okay? So finally, let's throw it into here. What do you get? So if you do 3 squared plus 5 squared plus 2 times 3 times 5 times this cosine thing, and the cosine thing, whatever you throw here, have all the nonsense digits that you have. Don't just have 98.13, like use the whole thing, whatever you got. What does it come out to? Now everyone is punching away. And while you're punching away, I'll say, if you wanted to know this with a nice formula with square roots, now I see you can do it. You use a trig formula. There's a way to expand out cosine of 45 plus theta. And if you expand out cosine of 45 plus theta, you actually get something that just involves cosine of theta and sine of theta. Cosine of theta is this nonsense. Sine of theta, you can use square root of 1 minus this thing squared. And so the whole thing can be written just with square roots, right? You can use the additive identity for cosine if you wanted to right here. So there is a way to write down an answer just with these square root symbols. Meanwhile, what do we have? We have c is square root of 58. Is it that nice? We have 7.61 is popping out. Okay, and you're telling me that that squares to 58? Can someone please take the 7.61577 and just square it? Is that going to give me 58? Like, what happens if you really take, someone has more digits, 7.61577. If you type that in and you just square 7.61577, oh, wow. So it is the square root of, oh, wait, it's close enough. That's so many nines. That's so many nines. I mean, if it's got 4 nines, then probably what's going on is that people are just, off by a little bit in the approximations. Okay, wait, but that tells us that the answer is square root 58. That means there's a nice way to do this problem. Okay, so that means that there's a nice way to do this problem. The answer is square root 58. Whoa, that's cool. Okay, so what I'll say is that the reason I wanted to do this out is that now you can see this is how you can bash the problem. We just bashed it with trigonometry. But now we're curious. There's a nice way. Nice way. Square root 58. I'm intrigued. How can I get this a nice way? Because if it's square root 58 and 3, so the reason, by the way, why my alarm bells are going off for like, there's something nice, is because 3 and 5 and 7 are totally random numbers. There's no reason in the world why 3, 5, and 7 should be able to give you a nice thing like square root 58 without it having a nice general thing. All right. Now we're going to go and try to figure out what could this be. Are there like other nice ways to see this? 3, 7, and 5. You definitely got me curious at this point. So there's some magical, the water is magical, that's right. And people are saying 58 is 49 plus 9. What? It's a right angle? No. Don't tell me you did that. Wait a second, that's nuts. So are you saying that we know this? How could that be? I mean, it has to be if that's the case, right? But like that's not always the case. So in that case, this is a really weird question. So I said that 3, 5, and 7, those are probably like random. But whoa, wait, let's check this guy out now. So did I just get unlucky in law of cosining that thing? If I law of cosine this guy instead, then presumably I'd have gotten the right triangle. And that's just not fair. I mean, that's not general. That's not general. It should not actually always be this way. You cannot just like say, I picked 3 random lengths and it's always going to be a right angle. So did someone just like really cook this problem or something? I should get 45 degrees if I do this. Well, let's see. Let's just see for fun. Yeah, for fun. I'm curious. Okay, this 3 root 2, 5, 7 triangle. I know we're way over time, but you can see this is what happens when I start doing a math problem. I just want to solve it. All right, so this 3 root 2, and then this 5, and then this 7, okay? I don't know what is this theta, but it's going to satisfy some law of cosines thing. So that means that if I take the 3 root 2 squared, which is 18, plus the 49 minus 2 times 3 root 2, that was supposed to be a 2, times 7 times cosine of the theta, that's supposed to be equal to 25. All right, let's go and start cleaning up. Someone's very excited. So let's go and move the cosines to the other side. Move the cosine to the other side. Now if the 18 plus the 49, anyone can do that fast? 18 plus 49, and then a minus the 25, divided by 2 times 3 root 2 times 7. So now 49 minus 25 is 24. 18 and 24 adds to 44. Is that right? Did I do that right? Maybe I can't do arithmetic. 24, no it doesn't. 24 plus 18 is not 44. It's 42, 42. Oh wow, 42. 42. Okay, so in that case, that's 42. So that's like 2 times 3 times 7. So cosine theta is 1 over root 2. Yes, 45 degrees. It's 45 degrees because the cosine of 45 degrees is square root 2. Shouldn't the thing be on the right-hand side be 25? No, because my theta is here now. Maybe it was confusing because I called it theta and the other was called theta. That is the worst thing ever to do. If you're ever teaching math, don't use the same variable for different things. Phi is what we always call these. Phi. Bingo. So we got these. So in that case, it's 45. So in that case, like, yeah, on this particular problem, this is just like a very weird right angle. But that's not true in general. So in that case, now I'm going to say it's now less clear to me that there's a general formula which is that nice. Gee. You really got me interested in this. So first of all, here's what I'm going to say. The solution that I showed you here is a solution that you can always use, whether it's 3, 5, and 7, or like pi, e, and not I, but like square root of 2. You can have like 3 nonsense numbers here. And if you have the 3 nonsense numbers, this rotate by 90 degrees, you will always get a 45, 45, 90 right triangle. So you'll always be able to write the square root 2 times it for that length. And then at that point, we'll be always able to use these 2 and that length to law of cosines that thing out. And once you law of cosines that thing out, you'll be able to add the 45 and then law of cosines one more time and get that. And in fact, as I said, there's even a way to write out an explicit formula for this by using the formulas to simplify the trigonometry of the cosine. Like you can explain this whole thing with just a's, b's, and c's and everything with all these square roots. So we could get an explicit formula if I wanted to. It's still pretty cool that the 3, 5, 7 gives you a right angle. I just think that's nifty. Okay, well with that, I think unfortunately that's it for the live stream for tonight. As some of you were asking, when's the next live stream going to be? I actually don't know. When the next one will come, I'll throw it back onto the channel. Just subscribe to this channel if you want to be notified of the next one. The reason that I'm quite busy now is because some of you know I've actually just opened an academy that runs training for high school students. Academy, it's like an online thing where what we're doing is we're helping high school students from all over the country, all over the world, learn communication skills while teaching mathematics. So this is because I wanted to provide a way for people who are in high school who are really, really good at math to go and learn how to have confidence and how to be good at speaking or good at streaming. And the best way to do that is by practicing. So what we did is we have this thing for high school students. And how do they practice? They actually practice by teaching classes of middle school students. So we have this running all around the country, all around the world right now, where we have middle school students who are taking math classes that we're running. And those math classes are being taught by high school students who want to be there because this is their chance to learn how to be a streamer. And of course, we also provide them with all of the know-how and the equipment to be able to stream like this. So basically, that's what I'm busy doing right now. And so there are all of these different high school students we're working with. In fact, tonight, during this particular live stream, we had one of our classes going with our high school students teaching middle school students. Oh, can you send a link? Actually, if you're curious, this exists. This is called live.poshenloh.com. That's just live.poshenloh.com. And it's not a high school math course. It's actually just something where people are working directly with me on this. Although actually the live.poshenloh.com, if you go there right now, what you'll see is that it's a link for the middle school people to sign up. Now, if you go and visit that same link, live.poshenloh.com, in like another day or two, what you're going to see is that that's also going to explain how the high school students can join. But basically, yeah, if you watched this far into this video, post-recording, or if you're live right here, if you just go there, you'll see it. Oh, yeah, another thing. I think that website has an email address you can email. If you just email that email address saying you just heard this on this live stream and you want to know how to get involved, we can definitely point you to how to apply. But this particular thing that I'm spending all of my time on nowadays is to try to find a way to help high school students who are really good at math to become really good communicators, while at the same time helping to teach middle school students who are looking for more than they can find in the school curriculum. So for the high school students, somebody's asking, is this free? It is, of course, free for the high school students. In fact, we actually even pay the high school students because they end up teaching the middle school students, and that's actually a service. So for the high school students, yes, actually it's more than free, but that's why it's competitive. So I have to go and I'm involved in trying to figure out how to do admissions for this thing, and then of course working with the high school students once they're in. But anyway, so that's what we've got. That's why I'm a little bit busy for a while. But there will be certain live streams that will pop on because, for example, I'm doing an official collaboration with various math competitions that we'll announce, and you'll hear about that. And then we'll be going over the problems here. Okay. Awesome. Well, I'm glad that you like the concept. And is it free for middle schoolers? No, it's not free for the middle schoolers because this is something that middle school students are paying for these courses all around the country and all around the world anyway. And so that particular part is not free. And that's actually why the high school students are also paid once that comes into that piece. But that's just what's going on over on another part of my life. I'll see you on this live stream again for other kinds of math competitions soon. Thank you to everyone for coming and making it all the way through in this entire series. I'll see you next time. Bye-bye.